little intro video that was from YouTube that I found. It's just a good opportunity for you to jog your memory before we get started today. We are going to be simplifying square roots today. So we will be using this idea of the factor tree, which we were practicing when we were doing some of our factoring back in one of the previous units. So the directions for example 1 are simplify the square root, assume all variables represent positive numbers. For this idea right here that all variables represent positive numbers, this idea is going to come into play in future mathematics classes. When you get to Math 3 into pre-calculus, this will no longer be a condition, and you'll have some more discussions about what happens when I have a negative variable underneath a radical. Okay. For now, they're trying to simplify things a little bit. So we're just going to assume that all of the variables are positive, and that kind of takes out some of the conditions that we would need to account for. Your directions for these types of problems might also say, use the product rule to simplify the radical, or simplify by factoring. We're going to do it all the same way. Okay, I'm not going to go over different rules for each one of those different directions when you can do them all the same way. So before we get started here, we need to talk about this idea of perfect squares. What is a perfect square and how do I identify it, right? So an example of a perfect square is 4. 4 is a perfect square. The reason it's a perfect square is because I can rewrite it as 2 squared, as some number to the power of 2. 9 is also a perfect square because I can rewrite this as 3 squared. And I can generate a whole list of these, right? In fact, it goes on forever and ever and ever. So 16 is a perfect square. 25 is a perfect square. 36 is a perfect square. 49 is a perfect square. 64 is a perfect square. It goes on and on and on and on and on. 169 is a perfect square. Okay. So what makes it a perfect square? 25 is the same as 5 squared. All right. When I'm talking square roots, I could take the square root of 25. Squaring something and taking the square root are inverse operations. When I take the square root of 25, I know 25 can be rewritten as 5 times 5, and that's just 5. Same thing here for 36, right? So the square root of 36 is equal to the square root of 6 times 6. I could even rewrite that as the square root of 6 squared and get 6. So I can think of it as a couple different ways. So basically, when I have these pairs here, it comes out and I just end up having one of them on the outside of the radical. And that's what we're gonna deal with here today. We're going to start with just some numbers, some positive integers here. And then in our next example, it's down here, E, F, and G, we're going to add some variables. So to start off with, let's look at 60. And let's do the factor tree for 60. What 2 numbers can I multiply to get 60? Other than 1 and 60, I need something else. So you could do 2 and 30, you could do 3 and 20, you could do a lot of different combinations. I'm going to go for 6 and 10 because that's the first one that pops into my brain. What are 2 numbers that multiply to 6? Well, 2 and 3. 2 and 3 are prime. All right. And let's go over the definition of a prime number. A prime number is a positive integer that is divisible only by 1 and itself. So the smallest prime number is actually 2 because it's divisible by 1 and 2. The opposite of prime is composite. 10 is not prime, it is composite. What two numbers multiply to 10? 2 and 5. 2 is prime, 5 is also prime. So I can rewrite the square root of 60 as 2 times 2 times 3 times 5. And I'm just multiplying these factors that I've got down here. Now I'm going to go through and I'm going to look for my pairs. Because the square root of 2 times 2, well, 2 times 2 is 4. What's the square root of 4? 2. So that comes outside the radical. Now there's a 3 in here, there's a 5 in here. Those don't have a pair, so I can't move them. They're going to stay inside the radical. And then to simplify, I'm just going to multiply whatever's on the outside with what's on the outside, and whatever's on the inside with what's on the inside. The outside will stay 2, and the inside I have 3 times 5, which is 15. So to simplify the square root of 60, I get 2 square root 15. Example B, the square root of 39. So for 39, I'm going to do the factor tree. And I need to find two numbers that multiply. Okay, I need to find two numbers that multiply to 39. All right, so let's see. 3 goes into 39. It goes in 13 times. 3 is prime. What two numbers multiply to 13? Nothing. 13's prime. So when I rewrite the square root of 39, I get 3 times 13. There's no pairs. There's no perfect squares inside of this. So there's nothing that I can bring out. Well, whatever's left inside, I just have to remultiply. So I get the square root of 39. And that's it. I can't simplify this. Okay. All right, so now with C, I have 3 times the square root of 64. So when I have a 3 out in front, I'm just going to leave the 3 in front, and then I'll rewrite the square root of 64 after I write down and do the factor tree. Now, some of you might look at that and go, oh, I know what the square root of 64 is. That's great. You can use that. But I'm going to do it. I'm going to go through all the steps here just in case we don't know what the square root of 64 is. So I need two numbers that multiply to 64. Other than 1 and 64. So I'm going to pick 8 and 8. If you picked 2 and 32, that's great. You can do it a different way. Let's see. 8 can be multiplied by doing 2 and 4. 4 I can get by multiplying 2 by 2. And then the same thing on the other side. So I tend to underline these little numbers when I know that they're prime, so I know that that's the end, right? I don't have to keep going. Whoa, that's a lot of 2s. 1, 2, 3, 4, 5, 6. Okay, so 2 times 2 times 2 times 2 times 2 times 2. That's a lot of them. 1, 2, 3, 4, 5, 6. Okay. So when I'm taking square roots, I'm looking for things in pairs. Okay, because when I take the square root of 2 times 2, I know that's really the square root of 4, which is 2. I have another pair of 2's. Right? So the square root of 4 is And then I've got another one yet. So I have a 3 in front times 2 times 2 times 2, which is just 8. Remember, you're multiplying. So 3 times 8 is 24. And I have no radical left, and that's okay. There was nothing left inside. It can just fall off. The square root of nothing is nothing. Now, again, I know some of you look at this and you're like, oh, the square root of 64. I know that's 8. 3 times 8 is 24. Boom. Good. Good for you. You can do it that way. It's totally fine. They don't all end up that pretty. All right. Question D. So I have an 8 in front again. And I need to take the square root of 48. I'm going to pause here and give you a head start to I'm going to give you a head start to try to after that. Okay, so when I break up 48, if you did it differently than me, that's totally fine. I'm going to use 4 and 12. 4 breaks down to 2 times 2. If you get the prime factorization, it's okay. What multiplies to 12? Let's do 3 and 4. 3 is prime. And then 4 breaks down to 2 times 2. So let's see, I've got a 2 and a 2 and a 2 and a 2 and a 3. All right, now I'm looking for pairs. So I've got a pair of 2s. So when I take the square root of 4, I get out a 2. I have another pair of 2s. I take the square root of 4, I get out another 2. And then I have a 3 left inside. So when I simplify that, I get 32 square root of 3. Okay, so to just give another explanation again, when I'm talking about the square root of 4 in here, I'm talking about if I were to multiply the 2 times 2, I would have 4 in here, right? So I'd taken the square root of 4. And the square root of 4 is just 2. So that comes out as one of the 2's. And the square root of 4 again is 2. That's why I have 2 2's out. So I have one for you to try now. your turn. Please go ahead and simplify the square root of 18. Go ahead and try that one on your own. Good. So when you take when you do your factor tree of 18, I see 2 and 9 first. I'm going to write that. And then I get a 3 and a 3. Okay. So when I rewrite my radical, I have 2 times 3 times 3. So you're looking for perfect squares, which means you're looking for pairs. Okay. So 2 doesn't have a pair, but the 3s do. They have a pair. That's your key. All right. Because 3 times 3 is 9. What's the square root of 9? 3. Right? Now the 2 doesn't have a pair, so it stays inside. So my answer here is just 3 radical 2. And if I were to type that in like a keyboard, I would just do 3 square root 2. Because my keyboard, my normal English keyboard doesn't have a square root key. The next thing we're going to do is we're going to add on some variables, all right? And I don't think that the variables make it any harder. You can let me know what you think. It makes it another step. I don't think it makes it any more difficult. All right. So for E, I'm going to do the factor tree for 27. Break this down. Well, the only things I can choose are 3 and 9, and 9 is just 3 and 3. So underneath my radical, I'm going to write 3 times 3 times 3. Then I have x to the 5th. X times x times x times x times x, right? I have 5 of them. If I'm raising something to the 5th power, like an x, I'm just multiplying by itself 5 times. So I'm going to go through and I'm going to look for pairs again. I have a pair of 3s. 3 times 3 is 9. What's the square root of 9? 3. So basically I have a pair. When I take the square root, I take one out. Here's a 3. It has no partner, so it stays inside. I have a pair of x's. When I take the square root of x times x, it comes out as an x. So the square root of x squared, or the square root of x times x, is still just going to be x. For the same reason. Now I have x times x here, so the square root of x times x is going to be x again. And then one more singleton left inside. So if it doesn't have a pair, leave it under the radical. Right? If it does have a pair, you bring one out. Now I'm going to multiply whatever is on the outside with what's on the outside. So that's going to be 3x by whatever's on the inside with what's on the inside, which is just 3x. So I get this, 3x squared times square root of 3x. And you're thinking, that doesn't look simplified. I know, but it is. All right, let's give F a try. So I'm going to pause here for a few seconds. Feel free to work ahead. Maybe you can figure that one out on your own. Square root of 100 h to the 6th. And if you're not ready to work it out on your own, then just wait a few seconds and I'll do it with you. Okay, so hopefully you gave it a shot. And if you didn't get all the way through, that's okay. Let's go ahead and do our factor tree. Now, again, if you know what the square root of 100 is and you don't feel like you have to do that, it's fine. Okay. If I start breaking this down, let's say I go 4, 5. Okay. You can use different numbers. That's fine. Maybe use 10 and 10. That's cool. 4 breaks down to 2 times 2, which are both prime. 25 breaks down into 5, which are both prime. So when I write these underneath the radical, I get 2 times 2 times 5 times 5. And then I have h to the 6th. So I need to write out h times itself 6 times. All right, then I'm looking for pairs. So I've got a pair of 2's. The square root of 2 times 2 is 2. The square root of 5 is 5. That leaves me with no more numbers underneath the radical. I have a pair of h's, so square root of h times h is h. Another pair. And another pair. That leaves me with absolutely nothing underneath the radical. Okay, so then just get rid of the radical. The square root of 0 is 0. The square root of 1 is 1. 2 times 5 is a 10, and then h times h times h is h cubed. So you get 10h cubed for that problem. Cool. Okay, we're going to go ahead and work through G, and then we're going to go on to the next example, which is really more of the same. So for G, I have a negative. So I'm going to write the negative 12 first, and then I need to write out all the factors inside. It's going to be quite a few of them. So I'll start with 75, do the factor tree of 75. For me, the first thing that comes to mind when I'm factoring 75 is 3 and 25. I think because of like 3/4 is 75 cents. And then 25 can be factored to 5 times 5. So for my numbers, I have 3 times 5 is 5. And then I have some variables in here. I have x to the 7. So I'm going to write x 7 times 4, 5, 6, 7. And y squared, so y twice. All right. I'm going through and I'm looking for perfect squares. So the 3 doesn't have a partner. It's not a perfect square. I have 2 5s though, so that's a perfect square. I can bring one of those out. I have a pair of, that's a perfect square, so I can bring one of those out. Another pair of x's. What else have I got? I've got another pair of x's. This x doesn't have a pair. And then I get a pair of y's. So don't forget to state what's still left inside. I have a 3 inside, and I have an x inside. All right. Then I'm going to multiply it all back together. Negative 12 times 5, so that's going to give me a negative 60. X times x times x is x cubed. And then a y times the square root of 3x. Woo! All of that. Okay. For example 2, multiply and simplify. Assume all variables in a radicand represent positive real numbers. So these are similar instructions to before. The only addition is now we have multiply, and then we have this addition of this vocabulary word called radicand. So let's talk about what a radicand is. So if I have the square root of some number, and in this section we're only dealing with square roots, we're not dealing with third roots or fourth roots or eighth roots or anything else, which we will get to later on in mathematics. This number or variable or term, okay, this is called the rad. And it's the term under the radical. Could also be an expression, but we're not going right now. So the radicand. It's the name for what's underneath the radical. For this exercise, multiply and simplify. There's a rule. I don't know what the name of the rule is. I could look it up. All right. It's probably like product of radicals or something. All right. So when I square root of a times the square root of b, I can, as long as they're both square roots, I can multiply them underneath the same radical. So in a, I'm going to do this a little color coordinated here. What I can do is I'm going to write out the prime factorization of x cubed and write out the prime factorization of 6x to the fourth, all underneath one radical. Now, I could multiply these together and get 96x to the seventh and then factor it, but that just makes more work for myself. All right, so I do the prime factorization of 16. And when I factor 16, I get 2 times 2 times 2 times 2. And then with the x cubed, x times x times x. Then I write out the prime factorization of 6. What two things multiply to 6? 2 and 3. Now I'm going to put this right underneath the same radical. I'm just going to multiply it to the previous terms. So I have 2 times 3 times, and then x to the fourth, x times x times x times x. I can just write them all underneath one radical. And then I go through and I look for pairs just the same. So I have 2 times 2. The square root of 4 is 2. Bring one out. I'm looking for pairs. They don't have to be next to each other. 2 times 2 gives me another perfect square. X times x gives me another perfect square. Then I have this x, but wait, I have more x's over here. So these two guys together can give me a perfect square, bring out an x. Let's see, I've got a 2 and a 3. Neither of those have a pair, that's okay. Another x's, right? And a lone x. So I've got a 2 and a 3 and an x on the inside. All right, so everything that's on the outside I multiply together, everything that's on the inside I multiply together. 2 times x times x times x gives me 4 cubed. And then 2 times 3 times x gives me 6x. Like I said before, you were like, no, I really want to multiply it. You could multiply what's underneath the radical and get 96x to the 7th and then factor that. But you're actually just creating a little bit more work for yourself. Not a lot, but a little, right? So you can either factor them separately and write them all underneath 1, or you could multiply and then factor this whole thing. You'll get the same thing. If I do this part in green, it actually creates a little bit more work. All right, pause in case you're getting caught up. Maybe you want to take a minute and try to work through problem B before I do it. Feel free. Go for it. You just want to take a little break and try to do that real quick. Okay, let's go ahead and go over the solution. So when I do my factor tree for 20, you should get 2 times 2 times 5. And then you've got an A. When I have A cubed, I have a 5, because 5 is already prime, and then A times A. Then I go through and I look for pairs. 2 times 2, so the square root of 4 gives me a 2. I can bring that out. 5 times 5, the square root of 5 times 5 is 5. I get 1 pair of A's and another pair of A's and nothing left inside the radical. So that means on the outside I have 2 times 5, which is 10. A times A, which is A squared. All right, we had a lot of people feel comfortable at that point. All right, so as previously stated, this exercise that we're doing on example 1 and example 2 is really going to be useful when we get into 4.4. In example 3, we're just going to get a taste of that right here using the Pythagorean. So let me offer you up a reminder of the Pythagorean theorem. You should have seen this before. There's no guarantee that you have. Okay. For a right triangle, a squared plus b squared equals c squared. Where a and b are lengths of legs, and is the length of the hypotenuse. Pythagorean theorem for a right triangle, a squared plus b squared equals c squared, where a and b are lengths of the legs and c is the length of the hypotenuse. This example asks us to use the Pythagorean theorem to find the unknown side of the right triangle. So I've got a right triangle. I know that because I've got this right angle symbol in one of the corners. The side across from the right angle is always my hypotenuse, C. So that's the side length that I'm looking for. So the other sides are called my legs, and one of them's A and one of them's B, and it doesn't really matter which way I could swap A and B, and that would be fine. All right, so for A, I'm going to plug in 10, so I have 10 squared. For B, I'm going to plug in 24, I get 24 squared. And then hypotenuse is just C still. Now these numbers are going to get a little big. That's okay. 10 squared, that's 10 times 10, that's 100. 24 squared is 576. If you need to pull out a calculator to do that, or if you need to do on your side scratch work 24 times 24 and multiply that all out, that's cool too. And then I add, so 100 and 576 gives me 676. Equals C squared. To get C by itself, I have to get rid of the squaring, the exponent. To do that, I use square roots. So I take the square root of both sides. Well, the square root of C times C is just going to be C, so that leaves me with a C on the right-hand side, assuming C is positive. And then I have to take the square root of 676. So this would probably require a factor tree. Oh, that's kind of a big number. What can go into 676? I would start with 2. I know 2 goes in there. And if you don't know how many times, then you can use a calculator to figure it out or do it by hand. 2 into 676 goes in 338 times. 2 is prime. Yay. Keep going over here, though. What can go into 338? 2 again. I like that. And it goes in 169 times. And in the beginning of our notes, we generated a bunch of perfect squares, And one of the ones that we generated was 13 squared, which happens to be 169. So that was convenient. 13 is prime. So when I rewrite this as a product of its factors, I get square root of 2 times 13 times 13. Pair of 2's gives me the square root of 4, which is 2. The square root of 13 times 13, which is the square root of 169, which is 13. And I get C is equal to 26 units. Usually when I put numbers in context, I have some kind of a units. This problem didn't give me any, but maybe 26, whatever my units are. Okay, and that wraps up the 4.3 notes. You'll want to practice this homework and then make sure that you're, for the next section for 4.4, we're going to be using these skills. So they're going to be important ones to have. Thank you for being present for these notes, and take care. Bye-bye.